linear equations. In this section, we'll see the method for solving what are called first-order linear differential equations. So first, a definition. A first-order linear differential equation is one that can be put into the form dy dx plus p of x times y is equal to q of x. Or we can write y prime instead of the dy dx. So consider this example. xy prime plus 3y is equal to x to the fifth. And again, we want to try to solve for y. We want to try to find what function, if possible, or generally what equation can be used to solve this equation. So notice that this is a first-order linear differential equation because I can divide through by x. If I divide through by x, I can write this equation in the form y prime plus 3 over x times y is equal to x to the fourth. And so it certainly fits this form that we've defined on this page. So now, to solve this equation, we use a little bit of a sort of magic. And I'll explain where the magic comes in shortly. But here's what we do at this point. We multiply both sides by something called an integrating factor. And in this case, the integrating factor is x cubed. Now, if I multiply through by x cubed, let's see what happens. I would now have x cubed y prime plus 3x squared y is equal to x to the seventh. Now, don't worry about where that x cubed came from right now. I'll explain that in the next slide. Just go ahead and accept it for now. So I multiplied through by that integrating factor, and now something nice happens. Let's look at the left-hand side of this equation. And you have to notice something here. If you look at this, this looks like the result of a derivative using a product rule. The left-hand side is the derivative with respect to x of x cubed y. And so when we have this linear differential equation and we multiply by that integrating factor, this nice thing happens every single time. We get this derivative that's a result of a product rule. And so, like we did with separable equations, at this point, we integrate both sides with respect to x. All right, so let me throw in a dx in here, a dx. We integrate both sides with respect to x. And so that would then yield x cubed y is equal to 1/8 x to the 8th plus a constant. And then, in this case, we can easily isolate y by simple division. Let me divide through by x cubed. And then y is equal to 1/8 x to the 5th plus c over x cubed. And there's the solution of the equation. So this is the technique that we can use to solve any first-order linear differential equation. We put it in the standard form. We multiply by this integrating factor. The left-hand side will become the derivative of using a product rule. So we integrate, and then we can isolate the y variable. So where did that I of x equals x cubed come from? Well, let's recall that we had the equation y prime plus p of x times y is equal to q of x. I of x, if we have a first-order linear differential equation, this integrating factor is defined as e to the integral of p of x dx. Now, in our example, the p of x was 3 over x. So then the integrating factor would be e to the integral of 3 over x dx. So integrating 3 over x, that would be 3 natural log x, which is the same as natural log of x cubed, and e raised to the natural log of x cubed is x cubed. So that's where that x cubed came from. And now in general, to solve the linear differential equation, y prime plus p of x times y equals q of x, multiply both sides by the integrating factor I of x equals e to the integral of p of x dx, and integrate both sides. So why don't you pause and try this one on your own? All right, so this looks like a linear DE. To put it in the standard form, I'll go ahead and divide through by t, yielding, this should be a dy dt, sorry about that. So I'll just write y prime plus 2ty equals t. I see that this is a linear DE. I put it in the standard form. Let's determine the integrating factor. I of x would be e to the integral of 2t dt, and so that would be e to the t square. So I'll multiply through by e to the t square, yielding e to the t square times y prime plus 2t e to the t square times y equals e to the t square times t. All right, now the left-hand side, if we've done this correctly, the left-hand side should be a derivative using a product rule. So let's see, this should be d by dt of e to the t square y. Let's just double check that. If I took the derivative with respect to t of e to the t square y, I'd have e to the t square times the derivative of y with respect to t. Okay, we'll write y prime for that. Plus, then I'd have to take the derivative of e to the t square. That would be e to the t square times the derivative of t square, which is 2t, and we'd leave the y alone, so that works out. So I'll integrate both sides, and I'll put in a dt just to be safe here. And so then that would yield e to the t square times y is equal to, now on this integral we have e to the t square times t dt. I think we have to use a substitution there. We'll let u equal t squared, then du is equal to 2t dt. So I would need a 2 and a 1/2 on the outside. And so then I'd have 1/2 e to the u du. So that's 1/2 e to the u plus a constant. And so that would be 1/2 e to the t square plus the constant. And then dividing through by e to the t square, I can write y is equal to 1/2 plus c e to the negative t square. Solve the initial value problem. 2xy prime plus y is equal to 6x, where x is positive and y of 4 is 20. All right, so remember, to solve an initial value problem, we basically just sort of solve the differential equation, and then we substitute the initial value to find the specific value of the constant of integration. So I'll put this in standard form by dividing through by 2x. So then that would yield y prime plus 1 over 2x times y is equal to 3. This is a linear first order in standard form. Let's find the integrating factor. E to the integral of 1 over 2x dx. All right, so let's see if we let u equal to 2x here. So that's 1/2. That's 1/2 times 1 over x. So that's e to the 1/2 natural log x. And so that's e to the natural log of x to the 1/2. And so that's x to the 1/2. So that's the square root of x. Let me multiply through by the square root of x. So I would then have square root of x times y prime plus square root of x times 1 over 2x. That would be square root of x over 2. Y is equal to 3 root x. Now, hold on. I forgot the x here. Right, there should be a 2x. When we reduce here between the root x over the x, that would leave a root x in the denominator. Now again, the left-hand side fits that pattern. This is d by dx of root x times y. So we will integrate both sides. Yielding root x times y, and integrating 3 times the square root of x, that would be 3x to the 3/2 over 3/2, plus a constant. So root x times y is equal to 3 divided by 3/2, that's 2x to the 3/2, plus a constant. Dividing through by the square root of x, y would equal 2. X to the 3/2 divided by x to the 1/2 would be just x. And then we'd have plus c over the square root of x. Now, using the initial value that y of 4 is 20, using the fact that y of 4 is 20, then we would have 20 is equal to 2 times 4 plus c over the square root of 4. So 20 is equal to 8 plus c over 2. And solving for c, subtracting 8 is 12, multiplying by 2. We find that c is 24. So our conclusion for the solution of the initial value problem is y is equal to 2x plus 24 over the square root of x. All right, here's another problem. This would be a good one for you to try on your own. All right, I've got x squared plus 1 dy dx plus 3x by y minus 1 is equal to 0. Now, this doesn't immediately look like a linear equation because I've got that y minus 1, right? This is causing a problem. So what I'm going to do is I'll leave the x squared plus 1 and I'm going to write y prime. Let me apply the distributive property here. Then I've got a 3xy minus 3x is 0. And now I'll add 3x to both sides. And now this looks like a linear equation. To put it in standard form, I'll divide through by the x squared plus 1. Yielding y prime plus 3x over x squared plus 1 times y is equal to 3x over x squared plus 1. Determining the integrating factor, right, the I of x, that would be e to the integral of 3x over x squared plus 1 dx. If we use a u substitution, if we let u equal x squared plus 1, then du is 2x. So I would need a 2 here and a 1/2 on the outside. And of course, I can bring the 3 outside. And so then that would end up being what, e to the 3/2 integral of 1 over u du, and so that's 3/2 natural log, that's e to the 3/2 natural log u, and so then that's 3/2 e to the so that would end up being u to the 3/2, and so then substituting back, that would be x squared plus 1 to the 3/2. So multiplying through, I would have x squared plus 1 to the 3/2 y prime plus 3x times x squared plus 1 to the 3/2 over x squared plus 1 times y is equal to 3x times x squared plus 1 to the 3/2 over x squared plus 1. All right, simplifying this a little bit, I would have x squared plus 1 to the 3/2 times y prime plus x squared plus 1 to the 3/2 over x squared plus 1. That would be what, 3x, and we'd have an x squared plus 1 to the 1/2 times y, and on the right hand side would be the same thing, 3x by x squared plus 1 to the 1/2. The left-hand side is the derivative with respect to x of x squared plus 1 to the 3/2 times y. So let's integrate both sides. So then I would have x squared plus 1 to the 3/2 times y. Now on the right-hand side, this looks like a substitution. If I think pretty much like I did before, if I let u equal x squared plus 1 and du equals 2x dx, then I would need a 2 on the inside, and I can bring a 3/2 on the outside. So this would end up being 3/2 x squared plus 1 to the 3/2 over 3/2. Plus a constant. So then I have x squared plus 1 to the 3/2 times y. 3/2 over 3/2, those go away. I've got an x squared plus 1 to the 3/2 plus the constant. And now I can solve for y. I divide through by the x squared plus 1 to the 3/2, and y is equal to 1 plus c over x squared plus 1 to the 3/2. Now y of 0 is equal to 2. So 2 would equal 1 plus c over 0 plus 1 to the 3/2. So 2 is equal to 1 plus c, and c is equal to 1. And so then our solution to the initial value problem is y is equal to 1 plus 1 over x squared plus 1 to the 3/2. So I was a little tricky with the actual calculus, but again, the same technique works every single time if we have an initial if we have a first order linear differential equation. Let's finish off this section with another mixture problem. Now, in the mixture problems we saw in the previous slide, in the previous section, we ended up with separable equations. Let's see what happens with this one. A tank contains 100 gallons of brine made by dissolving 60 pounds of salt in water. Salt water containing 1 pound of salt per gallon runs in at a rate of 2 gallons per minute, and the well-stirred mixture runs out at the rate of 3 gallons per minute. Find the amount of salt in the tank after 30 minutes. So notice the big difference here in this equation, in this problem, is the rate at which the solution is coming in and the rate at which it's going out are not the same. And generally, when that happens, we end up with a linear equation as opposed to a separable equation. So let's see what happens here. Like I did in the previous section, I will call A of t the amount of salt, and that'll be in pounds at time t, and that's in minutes. Do we have an initial value? A tank contains 100 gallons of brine made by dissolving 60 pounds of salt in the water. Salt and water. So that means that the initial value for A is 60. Alright, so let's remember that our equation takes the form dA dt, and again this would be in terms of pounds per minute. And we think rate in minus rate out. Alright, how is this coming in? Salt water containing 1 pound of salt per gallon runs in at a rate of 2 gallons per minute. So it's coming in at 2 gallons per minute. And it contains 1 pound of salt per gallon. 1 pound per gallon. Minus, how is it leaving? It's leaving at 3 gallons per minute. And at what's the amount of salt per gallon? Well, at any time t, there is A pounds of salt. Now, the tank starts at 100 gallons, but it doesn't stay at 100 gallons over time. Because in a sense, right, what's happening? It's coming in at 2 gallons per minute, and it's running out at 3 gallons per minute. So in a sense, it's losing 1 gallon per minute. Right? There's a loss of volume of 1 gallon per minute. So that affects the number of gallons leaving. And we can express that as 100 minus t gallons at any time t. All right, so it's always coming in at 1 pound per gallon, but for any time t, it's leaving at A pounds per 100 minus t gallons. So here's the equation we need to solve. dA dt is equal to, let's see, that would just end up being 2 minus 3 over 100 minus t times A. And this is a linear equation. Let me put it into the form we're used to seeing. dA dt is plus 3 over 100 minus t is equal to 2. All right, so now we have to find that integrating factor. And I forgot the A here. Sorry, there should be an A there. The integrating factor, I'll call it I of t in this case. I of t would be e to the integral of 3 over 100 minus t dt. All right, with a little bit of, with a little substitution here, we can write that as e to the negative 3 natural log of 100 minus t. We'll bring the negative 3 up, so that's e to the natural log of 100 minus t to the negative third. And so that's 100 minus t to the negative third. So I'll multiply through by that quantity. And so after simplification, we would have 100 minus t to the negative third. I'll just write a prime now. Now here, this is a 100 minus t to the negative first, so that's a plus 3 times 100 minus t to the negative fourth times a is equal to 2 times 100 minus t to the negative third. Integrating both sides, would yield 100 minus t to the negative third times a. Now on the right-hand side, let's see, just using a little bit of a substitution there, letting u equal 100 minus t. That's basically just u to the negative third, but we got to be careful here. We'd have what, if we let u equal 100 minus t, then du is negative dt. So we would need a negative and another negative on the outside, so this ends up being what, negative 2 integral of u to the negative third du. And so then that would be negative 2 u to the negative second over negative 2. Those go away. All right, so that would end up being 100 minus t to the negative second plus a constant. Dividing through by the 100 minus t to the negative third, which is the same as multiplying by 100 minus t to the positive third, we find that a of t is 100 minus t plus c times 100 minus t to the third. There's our general solution. Now, let's remember that we had an initial value. We said that a of 0 was 60. Let me get a little bit more room here. A of 0 was 60, so then that tells us that 60 would equal 100 minus 0 plus c times 100 minus 0 cubed. So 60 is equal to 100 plus 100 cubed times c. So negative 40 over 100 cubed is equal to c. And so that's negative 0.00004. So therefore, a of t is equal to 100 minus t minus 0.00004 by 100 minus t cubed. Now, there's our function, but let's go back up for a moment. We're not done. The actual problem asked us to find the amount of salt in the tank after 30 minutes. Well, now that we have the function, that's relatively easy. All right, so now the question is, what's a of 30? All right, what's the amount of salt after 30 minutes? Well, a of 30 would be 100 minus 30 minus 0.00004 by 100 minus 30 cubed. And so that would be 70 minus 0.00004 by 70 cubed, which I calculated to be 56.28 pounds. All right, that concludes this presentation.